We introduce our work about monocular 3D object detection. It's our fortune to publish this work in CVPR 2022. Now let's begin. As we know, monocular 3D object detection is a hybrid task comprising many subtasks. For obtaining a 3D box containing the target, we need to predict its class, the 3D center location, the dimension, and the orientation. Besides, estimating the 3D center location can further be divided into two subtasks. Estimating the pixel coordinate and depth of the 3D center. Previous publications indicate that depth estimation plays the most important part. In this work, we mainly study how to estimate depth well. Let's first recall existing depth estimation methods. There are mainly three kinds of methods: direct depth estimation, depth from height, and PNP. Although the detectors developed upon these three methods have obtained somewhat promising performance, it's still far from being satisfactory. Let us think what causes this. As I said, monocular depth estimation is an ill-posed problem, which means there doesn't exist abundant information for inferring depth. To bridge this information gap, almost all existing methods rely on some assumptions. When the assumption holds, the estimated depth is precise. If the assumptions collapse, the estimation becomes terrible. Now, let's think about how to address this problem. Since each depth estimation method depends on some assumptions, how about using different methods to estimate the depth of a target simultaneously? Assume such a paradigm. There are many methods depending on different assumptions and produce many diverse estimations. If any of the assumptions holds, it means that there exists at least one accurate depth estimation. If we can develop a good depth selector that can select out this accurate estimation, we can get a good monocular 3D object detector. So, how to produce multiple diverse depth estimations for each single target? Revisiting existing monocular depth estimation methods, we can observe that almost all of them can only produce one estimation for each target. Even though there is some work such as Monoface that predicts more than one estimation for each target, the estimation values are highly similar. To tackle this issue, we propose a method produces 16 diverse depth estimations for each target. Please refer to our paper for details. Then we use another two methods that produce 4 depths. Our detector generates 20 diverse estimations for each target. The following problem is how to select out the most accurate depths from all these 20 estimations. To realize this target, we regard each estimation as a Gaussian distribution and predict its uncertainty. In this way, we can remove the unreliable values based on the 3 sigma rule. Besides, we devise a strategy based on the EM algorithm. This strategy estimates the uncertainty of the unified Gaussian distribution and removes unreliable estimates iteratively. Using this strategy, we can select out the most promising estimation from 20 predicted depths and combine them into a single depth value. Please refer to our paper for the details. Moreover, in this work, we also study how to produce the 3D confidence better. We first observe that the uncertainty null without explicit supervision generalizes better. Hence, it's straightforward to use the estimated uncertainties to calculate the 3D confidence. Besides, we observe that combining the uncertainties of the depth estimation and core estimation leads to the best performance. Based on these observations, a new way of predicting the 3D confidence in monocular 3D object detection is proposed. We compare our method with the previous monocular 3D object detectors on KT3D. The results suggest that our method surpasses all the counterparts by large margins. For the car class in the KT3D testing set, our method obtains AP3D 70 scores of 70.14 for the moderate level. Besides, our method doesn't use any extra data and maintains real-time efficiency, which is about 25 frames per second. In addition, there is an interesting experiment result I want to highlight. In this experiment, we find that if this strategy becomes perfect, which means it always selects out the most precise estimation, the detection scores are almost doubled. This result further confirms the importance of diversity for monocular depth estimation. That's all. Thank you.